Welcome to this final session on offset well selection, submodule 3 of 3. In this submodule, we'll focus on how offset well data can be analysed to improve drilling performance. We'll cover stick charts, mud weight and pressure relationships, wellbore stability and data quality. Let's begin by setting out the learning objectives. In this submodule, we have 5 main objectives. First, we will recap our understanding of stick charts, which are vital tools for presenting offset well events in a structured way. Next, we'll focus on interpreting mud weight, pore pressure, and fracture gradient data to ensure we maintain safe drilling margins. We will then look at how offset data and caliper logs help us identify wellbore stability risks, such as hole enlargement or ovality. Another objective is to recognise key drilling events like stuck pipe, drag and fluid losses that directly affect performance and safety. Finally, we'll address data quality, understanding the limits of what's available, identifying inconsistencies, and ensuring we can rely on the information we base our designs on. Together, these objectives will build a strong foundation for optimising drilling programs by learning from offset well experience. Okay, let's do a recap on stick charts. These are a simple but powerful way to present offset well data. Their main purpose is to enhance the clarity of data presentation and reinforce the key message. While it's possible to plot all available information, sometimes a focused chart, say on casing seats, lost circulation or drag, gives us clearer insight into specific issues. For a stick chart to truly add value, formation depth should also be included. This allows us to link events directly to geological changes rather than only to measured depth. By aligning events with formation tops and bottoms, we can better understand whether issues are operational or geology driven. This is an example stick chart from drill plan focused on casing seats and associated drilling events. The vertical axis represents depth, while the plotted markers indicate events such as stuck pipe, circulation losses or reaming operations. By aligning these markers with casing setting depths, we can quickly identify correlations between problematic intervals and well-designed decisions. For instance, if repeated circulation losses occur just below a particular casing shoe across multiple wells, that signals a formation-driven issue rather than an isolated operational error. This type of visualization not only highlights recurring risks, but also provides insight into whether casing programs are optimized. By examining offset data in this structured way, we can improve future casing seat selection and minimize costly events. This example shows how stick charts can be applied to wells drilled through thick salt intervals. On the left side, we have depth in meters, and across the chart we see wells represented with event markers, such as lost circulation, stuck pipe, influxes, or reaming. The chart highlights both the top and base of the salt, making it clear where operational difficulties cluster. In deep salt environments, stick charts allow us to visualize the relationship between salt boundaries and drilling problems. For example, if several wells encounter stuck pipe near the base of salt, that suggests a stress transition zone that requires special attention in future designs. This type of offset well analysis transforms raw event data into a tool for predicting and preventing operational risks. Here we have a pressure depth plot showing mud weight, pore pressure and fracture gradient data across multiple wells. On the vertical axis we have depth, while the horizontal axis shows equivalent density in grams per cubic centimetre. Each curve represents either the planned mud weight, actual mud weights from various wells, or pressure test data like formation integrity tests and leak-off tests. By overlaying these curves, we can identify whether mud weights used in offset wells stayed within the safe drilling window, that is, above pore pressure but below fracture gradient. Deviations highlight risks such as well control incidents when mud weight was too low, or losses when it was too high. This type of comparative analysis is fundamental for refining mud programs. It shows us not only the safe operating window, but also how other operators navigated it. Here is an illustration of tripping history from an offset well. Tripping refers to pulling the drill string out of hole or running it back in, and it's a common source of wellbore stability and mechanical issues. By plotting depth against operational events, we can track where difficulties such as stuck pipe, drag, or losses occurred during trips. For example, high drag on pull-out or repeated clean-out trips may indicate unstable formations, tight hole conditions, or poor hole cleaning. These records provide direct evidence of how the wellbore responded mechanically under tripping loads. The value of analysing this history lies in recognising patterns. If multiple wells show fill on bottom at the same depth interval, we know that interval requires specific mitigation, perhaps by adjusting mud properties or improving hole cleaning practices. With tripping data understood, we can then extend the stick chart approach across multiple wells to compare operational performance. Here we see a stick chart that overlays operational events from several wells in the same field. On the vertical axis we have depth, while across the chart each well is represented with markers showing issues such as influx, gas cut mud, circulation losses, or drag. By comparing multiple wells side by side, we can quickly identify recurring problem zones. For instance, repeated losses while cementing casing at similar depths point to formation-specific issues. The chart also allows us to distinguish drilling fluid strategies. One well was drilled with water-based mud, while the others used oil-based mud from the 8.5-inch hole section onward. This difference provides valuable context when interpreting why certain wells experience more drag or losses. Multi-well stick charts are therefore powerful tools for field-wide learning, enabling us to extract best practices and avoid repeating costly mistakes. Offset well analysis provides rich insights into potential wellbore stability issues. There are several key indicators we look for. Stuck pipe events and their mechanisms are often the most obvious red flags. Caliper logs show hole enlargement, while notes on reaming or back reaming indicate unstable zones requiring frequent conditioning. Drag recorded during trips, especially when magnitude is high, signals tight hole or collapse tendencies. The presence of fill on bottom after tripping or cuttings and cavings observed over the shakers are further signs of poor stability. Fluid properties and mud weights are also essential. Changes in density can often be linked to instability. Finally, operational procedures such as hole cleaning practices or tripping speeds can exacerbate or mitigate these problems. By systematically analysing these factors from offset wells, we can forecast risks and plan preventative measures. Caliper logs are one of the most important tools for diagnosing wellbore stability. They measure the diameter of the wellbore and can also indicate the geometry of hole enlargement. There are several types available, ranging from single-arm calipers to more sophisticated multi-arm tools. A single arm provides basic borehole size, while two-arm logs, either single-axis or dual-axis, give additional dimensional detail. Four-arm and six-arm calipers, especially when arranged across multiple axes, can reveal not just the extent, but also the shape of enlargement. LWD calipers add the advantage of real-time data while drilling. Multi-axis calipers are particularly valuable because they help us distinguish between instability caused by chemical effects such as shale swelling and stress-induced effects such as ovality. By understanding the type of instability, we can choose the right mitigation strategy. This is an example of a single-axis caliper log taken from a well drilled with oil-based mud. The track indicates a uniform, almost perfectly cylindrical borehole, commonly described as a gun barrel hole. Oil-based mud systems often minimize chemical interactions with shales, which helps preserve gauge hole conditions. In this case, the caliper confirms minimal enlargement and no evidence of ovality or collapse. The log demonstrates the value of matching mud type to formation challenges. However, single-axis data is limited as it cannot detect directional enlargement or stress-related deformation. For that, we need to look at multi-arm caliper data. Here we see a 6-arm caliper log run in a 12 1/4 inch hole. The traces from each axis reveal an oval-shaped borehole, which is a clear indicator of stress-induced instability. In addition, the log correlates with gamma ray readings that differentiate sand from shale. Ovality observed within the sand interval highlights that instability is not only chemical but also mechanical. Multi-arm calipers provide a much richer picture of wellbore condition than single-axis tools. By quantifying both the magnitude and geometry of enlargement, we can link the instability mechanism to formation properties and stress regimes. This makes them critical for planning mud weight windows and well trajectory design. With caliper data understood, we'll now address another vital aspect of offset analysis, ensuring data quality. So far, it has been assumed that the data selected is correct and available. However, this is not always the case. Therefore, assumptions and interpretations of data quality need to be made. As will be seen in Module 2.2 on risk analysis, the quality of the data used can have a significant effect on the outcomes and predicted performance. In recent history, many companies have established standards for data quality, and well-generated data is checked prior to databasing or archiving. However, does this ensure the quality of the data? Possibly not, since reporting can be subjective and used to cover up or misinterpret certain events. To ensure data accuracy, redundancy in interpretation is required. Thus, as mentioned earlier, all available data should be utilized in offset analysis. By following the accident investigation process in Module 2.2, where data is queried, any subjectively reported events can be highlighted quickly. The application of redundancy in data being queried should be considered, as real-time domain data can provide a more detailed and granular comparison to reports, offering higher definition, see Module 2.3, and enabling the assessment of interpretations in other reports. Data viewing and analysis software are available to aid this process. An additional technique is a post-drilling a peer review report, which is generated by a senior engineer from a different team and can be used to highlight inconsistencies. Unfortunately, there is little that can be done about missing data other than to look at potential different sources, if available. Should a whole section of data be missing from the offset field data, then a conservative approach should be taken where stricter design factors and procedures are put in place until execution recovers data to prove otherwise, as per a wildcat-type design process. Let's review the objectives we set at the start of this sub-module. First, we aim to understand stick charts for offset well event analysis, and we achieved that by looking at examples ranging from casing seats to deep salt drilling. Second, we set out to interpret mud weight, pore pressure, and fracture gradient data, which we did through comparative pressure depth plots. Third, we explored wellbore stability risks, examining both offset events and caliper log examples to illustrate enlargement mechanisms. Fourth, we focused on recognizing drilling events such as stuck pipe, drag, and losses through tripping history and multi-well charts. Finally, we assessed data quality, discussing why assumptions can fail and how review processes safeguard reliability. Each of these objectives has been addressed with practical examples, reinforcing how offset well selection drives better drilling optimization. With this review complete, let's close the session. This concludes sub-module 3 of 3 on offset well selection. Please proceed to the quiz to test your understanding of the concepts we've covered. Thank you for your time and participation.